Hey everybody, hope you're having a great day today. My name is Lieutenant Bob Roberts. I'm with the Greenville, South Carolina Composite Squadron. Today we are going to be talking about aircraft engines, everything about aircraft engines, all about our aircraft engines. We are specifically going over the text for Aerospace Dimensions, Module 2, Chapter 1. And with that, let's just jump right into it. There's a lot to cover today. All right, so the first thing we want to talk about is we are going to be talking about engines again. We are looking at Chapter 1. What we are not going to be talking about today is we are not going to be talking about instruments or GPS. We are, however, going to be discussing that in our next video. With that, let's continue right into it. All right, so here are the outcomes that we want to look at. We want to look at how to be able to explain how a reciprocating engine works, identify the parts of the airplane engine when viewed externally. We want to describe how a jet engine operates. Identify the basic cockpit-mounted power plant controls, and identify the basic flight instruments. Now, as I had mentioned, we are going to be doing the basic flight instruments in the next video, but we are going to be covering a lot of this in this video. Okay? All right, so there are 4 forces of flight. We have reality, money, dreams, and the FAA. No, I'm just kidding. Those might be my 4 forces of flight. The real 4 forces of flight, we have gravity, thrust, lift, and drag. And so we can't affect drag too much. We either rent the airplane or we fly the airplane or we don't. We can't really affect lift too much. The airplane has the wings it has when we get into it. And we can't affect gravity unless we go to Mars. If we're on the Earth, gravity is what gravity is. What we can control is we can control thrust. And so that is the basis of what we're going to be talking about today. All right, so in general aviation, we typically control thrust by spinning a propeller in the air. And that pulls the aircraft forward. Now, the spinning propeller does send some air behind it, but not a great deal. The majority of the time that you feel that is when you're on the takeoff. You'll feel the air pushing from the propeller. You'll feel it push on the rudder a little bit. And you have to kind of kick the rudder a little bit as you're taking off. But otherwise, you're just kind of going forward and that propeller is pulling you in. All right. Now, so there is the engines that we use are called reciprocating engines, otherwise known as an internal combustion engine. This is very similar to most of the engines that you have in your cars. As an example, this individual that is starting this engine up here, this actually is a modified V8, car engine. So he was trying to get something to work for an airplane he was building and didn't spend all the money on an airplane engine. Don't know that I would agree. I don't know if I would feel comfortable flying in that, but it shows it works. So, all right. Now, one thing a lot of folks think is that oil comes from dead dinosaurs. And that's not the case. So oil actually comes from little tiny bacteria. And here you can see in this video them kind of like, vibrating around here. So you would think, okay, little bacteria that couldn't have produced that much oil. However, that's not the case. These things lived in just incredibly massive colonies. They only lived a short amount of time. So what did that mean? That meant you had constant growth of these dead mats. That's what they would call. Now, these dead mats could weigh millions of tons, just significantly more than what the dinosaurs would have weighed. And so these actually decomposed over time and became oil. And now we're talking about a long time ago. We're talking about 3 billion with a B years. There's a lot of zeros there. So now, once we get that, we have to then go into what we're going to use that fuel for. Now, we use in airplanes what is called a 4-cycle engine. And so the first thing we want to do is we want to put that fuel into the chamber, the combustion chamber. Now, that's an important word. You're going to want to know the combustion chamber. And so as we look here, the fuel comes in, and that's a first stroke, second stroke, third stroke, and then the fourth stroke. Now, if we take a look at this and we break it down even slower, that first stroke is called the intake. We can see the valve opened up and the fuel came in. And now we're going to go to the stroke 2. Stroke 2 is the compression stroke. Now, the compression stroke, we're going to see the piston slowly moving up. Now, obviously, in real life, this happens really fast. It's going to compress that fuel and air. And then, after the compression stroke finishes, we have ignition. from the very top of the spark plug. That causes it to basically burn, explode, however you want to say it. Hopefully it's not an explosion. And we call that the power stroke. It's also called the combustion, but we call it the power stroke. And then the fourth one, after it's been burned, we have to push it back up, and it's going to push it out another open valve. And so we call it the exhaust stroke, exhaust strike cycle. So that is our 4 strokes of the engine. Okay. Now that we have the engine and its 4 strokes, we have basically 2 types of engines. We have an inline engine as well as a radial engine. Most of our engines that we use today are inline. We have in our cars, we use either horizontally opposed or we will use a V. My truck is a V8, so it looks like that. It's the shape of a V. And then, but if we look at some other engines, we look at the radial, some of the older engines. And we're going to talk about some of the advantages here in a second of those. So exam tip, just remember, you have the upright, the V, and horizontally. Those are all inline. Your radial engine is not an inline. Okay? So general aviation, we typically use horizontally opposed inlines. This is a very reliable engine. It also makes it very compact. You'll notice that it's very flat, almost like a pizza box. But the downside is that the back cylinders, they don't have the air rushing over them the way that the front cylinder does. And so that does affect cooling, and power is reduced in order to not overheat the engine. If you looked at the old World War II airplanes, they could actually push the engines a little harder for a short amount of times if they knew that they could cool the engine off afterward. Also, exam tip for you those taking the Module 2 exam, a power plant refers to the entire engine and its accessories. Okay, so now we talked about the radial engine. This is a video of the radial engine. I am actually still a huge fan of this engine. As you can see here, all the cylinders are in a circle, so they're radial. And it's really neat. Now, if you look right here, you can see this is where the actual shaft would be. That part's not going around and around in a weird, funky shape. That's staying steady. Now, the actual shaft and how the actual engine works is all exactly the same. The only difference is that instead of it being in a straight line, it is all around in one spot. Now, the benefit of that. So the benefit of that is each cylinder has its own incoming air. So air that's coming into the cowling, coming into the front of the aircraft, it is every single one of those cylinders is getting all of that. Now the downside to that, if we look at the very beginning of that video, is the size, right? This thing is a honking piece of metal that's in the very front of the aircraft. So when we look at drag on the airplane, the radial engine causes a lot of drag. Okay? All right. So again, the exam tips, the movement of the shaft from one end to the other end is called the stroke. And when we complete all the cycles, when we complete all 4 of those strokes, it is 1 cycle. And so even though a radial is still a 4-stroke. So 1 time around is still a cycle. Okay. All right. In addition to a reciprocating engine, we have 2 other types of engines that are typically used. We have jet engines and we have rockets. Okay, so this is a great diagram, thank you to Pratt & Whitney, for a jet engine. So we have similar cycles here. So a jet engine still has air that comes in, it gets mixed with fuel, it gets compressed, it gets ignited, and then that gets exhausted. The difference is that in a 4-cycle engine, a 4-stroke engine, the actual combustion of the fuel is what causes the power when it pushes down for the next stroke. However, with a jet engine, it's actually the exhaust. It's the speeding up of the air and the exhaust that actually causes the thrust, not the actual stroke itself. And then that push out is what actually gives us our thrust, and not the spinning of the vanes. The spinning of the vanes compresses the air, makes it move faster through the back. Okay. All right. A jet engine, pretty much totally different. However, the main difference here is that since you are going into space, you don't have any oxygen, right? So you can't mix the fuel with the oxygen in the atmosphere, what you have to do is you have to take the oxygen with you. Now, different rockets, different motor designs, they will tend to use different types of fuels, but typically they still have an oxidizer. They still have some type of oxygen. The other thing that you could use is you have what's called a solid rocket booster, and that's actually what that video just showed with the little rockets on the side. A lot of bigger rockets will use these solid rocket boosters. They have basically their fuel and everything that they need is mixed into the chemistry. It is a solid piece, and you basically just light it like you would a fuse, and it's just going to burn. The downside with a solid rocket motor is that once you light it, you can't turn it off. You're going. So if you're on that rocket and you launch that solid rocket motor, just hang on. You're going for a ride. With the liquid propellant fuels that mix with oxygen, you actually can control. You can throttle it back just like a car. You can step on the gas, or you can let it loose a little bit and pull back on the gas. And that's really important because there's different phases of the flight where you would want more thrust, and then there's other areas of flight where you would want less thrust. And so that's it. So that's the main difference. Rockets, they carry their oxygens with them. Okay. Now, fuel tanks. So fuel tanks are located in two spots on most general aviation aircraft. They are located either under the wing, as an example here with this Piper, or they are located above the wing, as is the case with Cessna. Most aircraft in Civil Air Patrol are Cessna-type aircraft, and their fuel tanks are above the wing. And so when the fuel is below the wing, you need a little pump that basically lifts the fuel to the engine. And if you have an above-wing aircraft, the advantage there is that gravity is going to do all that work for us. It's actually going to allow gravity to pull that fuel into the engine. So you have one less thing that can go wrong. One of the advantages of a low-wing airplane, that actually why people would use low wings as opposed to high wings, is that when you're flying it, you have good visibility above you. Now for Civil Air Patrol, we do a lot of search and rescue. So for us, you have good visibility below us. We don't have the wing blocking our view. So if we have observers, we can see the ground below us. Most training aircraft, although you definitely can train in a Piper, lots of people train in Pipers, but a lot of training aircraft tend to be high wings. You can see the ground better. You can look for the airport. You can look for basically ground references in order to line up your approaches, things of that nature. So it makes it a little bit easier when you're doing initial flight training to use a high wing. But again, you don't have to worry about a fuel pump. It's just going to draw it by gravity. Okay, and these are called gravity-fed fuel systems for your exam tip. Okay, now here's a really good picture of the above-wing gravity-fed fuel system. You can see the two fuel tanks on the wings here, and you can see basically the line that's going to go down into a fuel selector valve. The fuel selector valve then goes into a strainer because you don't want dirty gas going into your engine. That then moves into what's called a carburetor. We're going to talk about that in a second. Now, many of you, if you're younger, don't know what a carburetor is. I asked my children who are teenagers this question. Both of them drive, if they knew what a carburetor was, and they had no idea. I asked my daughter, her boyfriend's, if he knew what a carburetor was. He didn't know. So we're going to talk about what a carburetor is, since you may not know what it is. One important thing here I do want to talk about for those of you that are looking to learn how to fly is that fuel selector valve. Super important. If you're in a Cessna, you can set it to both, and then you don't have to worry about it again. If you're in a Piper or some type of other aircraft where you have to do a left or right selection, you want to make sure you don't forget about that. You want to make sure you have good management of that. A lot of pilots, unfortunately, lose their airplanes, and sometimes they lose themselves because they didn't have good fuel management. There was a gentleman up in Rochester, New York, and I'm not going to say his name for his own credit, but unfortunately, he's no longer with us. And the main reason why was he crashed an airplane because he didn't switch the fuel selector. He had one tank which was completely empty, and the other tank had I don't know how much fuel, but it had enough fuel for him to land. And so he was on his landing approach, and he ran out of fuel, and the engine, basically died on him before he got to the runway. So very, very sad. And this is not a rookie pilot. This was somebody that actually owned a flight school. up in Rochester, New York. Very experienced pilot, FAA examiner, all those things. So, no matter if you've been flying for 10 hours, 100 hours, 1,000 hours, thousands of hours, make sure you have good fuel control. Okay? All right. Next thing we want to look at is this carburetor. So a carburetor works, basically it's a device that mixes the air and the fuel together. And we actually have another picture here in a second showing it a little bit better. But the way that it works is that when we have that stroke of the piston, when that piston moves down, it causes low bed pressure. It's basically sucking that air down. And so when it does suck that air down, it basically just draws. So it's basically pulling, that stroke comes down and it's basically just sucking the air with it. And since the air is part of the carburetor, it's getting the fuel mixed into that airstream, and it's just basically pulling it into the carburetor. And so that's how we get the fuel in. And again, carburetors, they meter the amount of fuel that's going into the engine. Okay. Let's go to the next screen here. All right, so this is a good example. This is a good side drawing of a carburetor. And here we can see, here's where the fuel is located. There's a fuel screen, and there's a float and a needle valve that controls all this, regulates how much fuel is coming in from the main tanks. And then that fuel comes up, it gets accelerated up, and then we will see it injected into the airstream with the air coming up from behind it. So this is the air coming in, the fuel comes in, it gets mixed, it gets thrown basically into the airstream. And then, we talk about the Venturi effect. I'm not going to go into a Venturi effect here, but, if you look at how a wing works, if you look at how your propeller works, that low and high pressure, we're doing the exact same thing here. We're speeding up that air across for the Venturi effect. And then the throttle, this is basically what you're controlling inside of the airplane. You're opening and closing this. The more you close it, the less fuel and air you have going into the engine. The more you open it, the more fuel and air you have going into the engine. Okay? And again, the throttle controls the amount of fuel after it was mixed with the air. So exam tip there for you. Okay, so the fuel mixture itself. Now, if you had a lot of air and not a lot of fuel, that would be unburnable. There wouldn't be enough fuel into the air when it goes in the engine. But the opposite is true. If you had too much fuel, you would be too saturated, too rich, and you would flood the engine basically. In the engine actually wouldn't have enough air mixed with the fuel to burn. And so what we do is we look for the correct ratio. So this is called the Stoichiometric Ratio. And the ideal ratio is 15 parts per 1. If you're taking the test, you want to remember that. 15 parts of air for every 1 part of fuel. So that's your ideal. Now, as you get higher and higher, there's going to be less air per volume. And so you actually want to lean out the engine a little bit. Otherwise, as you get higher, you'll have less air and more fuel, so you'll get too rich. Now, you have to remember that when you're landing, if you just left it like that, you would be getting more air for the same amount of fuel. And so you would be getting more lean. Some pilots, when they land, their engines are running really rough. And the reason why is because they leaned out their fuel when they got up high to get better, gas mileage, basically. But then when they landed, they forgot to change it again. So you want to be able to do that. The other thing, too, is that when you are flying, you can lean the mixture a little bit, but that can cause your engine to run a little hot. And then what you want to do is you just want to rinse it. You want to make it a little bit more rich, and that'll cool your engine off a little bit. It'll actually put some of the heat of the engine into the fuel. Now, you may be throwing some fuel that is unburned, but that's one way you can cool off an engine a little bit. Okay? But again, if you're taking the test, 15 parts of air per 1 part of fuel. Okay? All right. So the other thing you want to look at is carb heat. So in your carburetor, because you're mixing the fuel in the air, when you're up and it's really cold, especially if you've leaned out the engine, that fuel can actually freeze. There can actually be some moisture as part of that fuel, and you will start to see your engine power coming down. Now, you just saw the individual here. He pulled out the carb heat, that little knob in the middle. And so what that will do is that will redirect some of the hot air from the exhaust of the engine back into the carburetor. And you'll see here in just a second, you'll see how quickly that ice is going to melt. And while that ice is melting, that water is going to be going into the engine. Your engine will start to run rough. It won't stutter or stop on you most likely, but it will. You'll basically see the engine RPMs coming down. If you're in a fixed prop aircraft, you'll see the engine RPMs coming down, but that roughness will only last for a short amount of time. And then you'll actually feel it get smooth again, and you'll see your RPMs come up slightly again. And then what you want to do is you want to turn off the carb heat. You don't want to leave your carb heat on all the time. Now I come from an area that's very cold, and so we would be in a bad habit of turning that thing on sometimes because we would really be worried about carb heat. But it does two things. One, you're adding preheated exhaust heat into your engine. That's not good. You want to keep your engine cool if you can. It runs better. And then the other thing too is because you're adding a lighter density air, your mixture is going to be different, and actually messes up with your fuel ratio. So you want to make sure that you don't do that too much. So only put it on when you need it, but don't hesitate to put it on and then turn it off. Again, if you're in a cold environment or an area where you expect that there might be icing, if you start to feel the engine not performing the way you would think, then go ahead and turn it on. If it's running smooth after you turn it on, just go ahead and turn it right back off. There's no penalty for you, really, if you do it in short bouts. Okay. Let's see. Now, one of the last things we have to talk about is oil. So, right now we have metal on metal. So that's not good, right? You're running super high speeds, and that metal on metal, it would basically cause it to get super duper hot, and they would basically seize. It would basically melt the metal to metal. And so what the oil does is it causes a little thin barrier between the metal and metal. And then that oil also gets sprayed up onto the camshaft, and then that will coat the walls of the combustion chamber itself, as well as the piston. And again, all the cylinders, the O-rings, it'll basically put some oil and all there. Now the O-rings, that's actually what the O-rings is doing. The O-rings is stopping the oil from mixing with the fuel. If you know me from Greenville, South Carolina, ask me about a runaway diesel detonation on an engine. We had an engine that we had a problem with. Oil was getting into the combustion chamber, and even though we turned off the engine kept running. we couldn't get the engine to turn off for about 10 or 15 minutes. It was very scary. But ask me that story if you know me personally. I'd love to tell it to you. All right, so that's oil. Okay. Now, magnetos. So similar to a car, we have spark plugs. One of the big differences is how we actually do it. So a car will have one spark plug per combustion chamber. In an aircraft, almost all aircrafts, we have two. And we do that for a couple of reasons. The first reason is that if we have a single spark plug, it has one spot to basically burn the fuel. If we have two spark plugs and they're on angles, well, now we have two areas and we have a better distribution, a smoother distribution of that burning of the gas. And so that's we want to make sure that helps our fuel economy. The other thing that it does is then it allows us to have a left magneto and a right magneto. Now, all that a magneto is a spinning motor, and then when it spins, it causes an electrical discharge. The electrical discharge goes to the spark plug, and that's actually what gives you your spark during the ignition phase, or during the combustion phase. All right, so that's important. The other thing it does is it gives us safety. So if one of these magnetos failed, let's say if this left magneto here failed on you, you would still have the right magneto. Now, when you're doing your pre-takeoff check of your engine, one of the things you're going to do is you're going to rev up the engine to a pretty good speed. Usually if you're in a Cessna, it's around 1,700 to 2,200 RPMs, depending on your engine. And then what you're going to do is you're actually going to, instead of running it on both, which is the default, you're going to actually choose. You're going to choose right or you're going to choose left. And then you're going to actually look at the RPMs. The RPMs, they will actually come down. You'll actually see the RPMs in your aircraft come down a little bit. Again, this is assuming you're in a fixed aircraft, fixed prop, so the prop doesn't change. But you will see the RPMs come down. Now, what you want to look for is you want to make sure they don't come down a lot. If they come down a lot, that means possibly one of your spark plugs is bad, or possibly one side of the magnetos is bad. You want to go get that checked out. But you should only come down a little bit. Usually it's around 50 to 75 RPMs, and then you'll turn it back up to both. Make sure the engine goes full back up. Then go to the other side that you didn't check previously. So if you were left initially, now you'll go to right. And then again, you should see a small dip, 50 to 75. Your pilot's operating handbook will actually tell you the exact amount you should be looking for. And then, and then once that works, then you should be good, and you can continue on with your takeoff. Now, this isn't. Some people that are in a hurry don't do this, and that's a little crazy. It only takes a couple of seconds to actually do this check. And I don't know about you, but I always tell folks, you're much better off being on the ground, hoping you were in the air, than being in the air and hoping you were on the ground. So if you're going to have an engine issue, you want to make sure you do everything you can to identify those issues before you actually take off. Okay? All right. So again, we are almost done. You guys are doing great. This is kind of a longer video, a ton of information, but you're all doing great. All right, so we really have a couple of controls inside. So the black knob is typically on the left, and that is our fuel to air mixture. I'm sorry. I'm sorry. Okay, I read that wrong, but I wrote it right. So that is our fuel throttle. So when you push it in, it actually is adding more, or it's reducing the amount of the total fuel to air mixture that's already been mixed in the carburetor. And we saw a picture of that earlier. Now, the red knob is actually what you would control the amount of fuel for a given ratio of air. So you have a certain amount of air coming in, no matter what, basically. And the red knob will actually add, or it'll add more fuel to that air, or it'll add less fuel. And then once that is all mixed, then your black knob is actually what you control the power. That's how much of that fuel to air mixture actually goes into the engine to be burned. When all that is done, the tachometer will actually tell you how fast that engine is spinning. So here you can see that, hey, 2200 RPMs, 2,200 RPMs is the start of that green arc, going up to just a little bit past 2,500 RPMs. And you can run it a little bit faster if you need to, but you're going to go into the yellow and then the red you never want to cross. But your normal flying power will be sometimes between 2,200 RPMs and 2,500 RPMs. Now, that's actually one of the things that makes a car engine different from an airplane engine. Car engines will run, obviously, very, very nicely, in that same range as well. The give or take 2,000 to 2,500 range. But you'll notice in a car that most of the time it will actually gear down. Actually, it would be the opposite. It would gear up. And the RPMs on the engine would actually be reduced. You won't see a car engine sit at 2,200 RPMs the whole time. So the advantage with an aircraft engine is it actually maintains a higher RPM than, say, you would see a car. Thought that was interesting for you to know. Okay. And so we are actually at the end of this video series. Great job. We are right at 28 minutes. So before we finish, I just wanted to let you know a couple things. So first of all, if you are a CAP cadet and you are using this information to help you study for the exam, here's what you should be doing, in my opinion. You should read the material first. When you are reading the material, go ahead and make some highlights to that, and make some notes on the pages, and then watch this video series. This video series will fill in the gaps of what you read. This is actually a very detailed chapter. Very detailed module and chapter, more so than what you've probably have seen so far in the other modules so far. So take your time with this. Don't feel like you have to know this all in one day. You really want to just try to learn a little bit every day and then learn a little bit more the next day. And I know that you will do fantastic. There is some hands-on exercises as well inside of the book. And these are going to really be something that after you've read the material and after you've watched these videos, those hands-on exercises are really going to cement into your brain all this information. And then once you are done with that, normally I would say go and take that test, but you still have one more to do. You still have to do the other part of this video, which I'm actually going to be uploading in just a few days. So chances are when you watch this video, go ahead and look. The second part of this is already up online. There is some important terms. Now, we've talked about all of these, so we'll just go through them really quick. Combustion, that is the chemical process of burning. The chamber, that's the enclosed area we saw that the fuel and air that went into with the spark plug igniting it. That's the combustion chamber. Compression, that's where we saw the fuel and air get compressed as the cycle came up. The cycle is the whole 4 strokes. It's the intake, compression, power. In Civil Patrol, we say power cycle and or power stroke, and then the exhaust. The fuel, that's where your gasoline or kerosene or propane or whatever you're going to use to burn in the engine. And then you have your lean mixture. Later on, we have the rich mixture. We talked about that. Magnetos, we talked about the little generator that produces the spark. And then the metering, that's we talked about the carburetor and how that meters the amount of fuel that gets mixed into the air. The power plant, we said, was the whole airplane engine and its accessories. Reciprocating engines get their name because there's a back and forth movement of the internal parts. And then we already talked about rich mixture, stoichiometric. Let me say that word again. Stoichiometric is the ration of fuel to air, and the stoichiometric ideally is 15 parts of air for 1 part of fuel. And then the stroke. So the stroke is when the piston will go all the way from its very top all the way to its very bottom. That is considered 1 stroke. So we talk about a 4-stroke engine. 1 cycle has basically, it'll go 1, 2, 3, 4, as we showed in the video earlier. All right, so with that, you are almost done with chapter 1. As I mentioned, there is a ton of information in this chapter, in this module. So please go back and review this a couple times if you need to. Don't feel like you didn't get it on the first shot. And other than that, I know you've got this. So hang in there and learn about engines. I'll tell you what, if you if nothing else, if you learn about a carburetor, you're probably going to know more than the majority of your friends about a car engine, or especially an aircraft engine, but even a car engine, the older fashioned car engine. So with that, we are done. I hope you've all learned something, and we'll see you on the next video. Talk to you soon. Bye-bye.